Okay, let's move on to A3, which is slightly different from the previous ones because now we have a piecewise function. What does a piecewise function mean? Explained simply, not rigorously, but just like in regular terms, it's a function that has at least two different expressions for different possible values of x, right? It's not just one expression that you use to calculate for all x's. There's like two or more options for it, right? That's how you can recognize a piecewise defined function, and it typically uses that curly brace in order to just mention all of the expressions for the different ranges. So in this case, we have a function that has this expression for any x different from 1, but specifically at x equals 1, it's equal to 2. We don't have to calculate it at x equals 1, right? And then we're asked to check if it's continuous over the whole range of real numbers, okay? Now, whenever you have a piecewise defined function, the boundary values, in this case we have one boundary value which is just 1, are always sort of like suspicious points that you should check for discontinuity in, okay? So if you had more ranges, if you had, I don't know, a boundary value at 2, at 5, whatever, you need to inspect these automatically, right? So the way it works for piecewise defined function and for these boundary values is we actually need to also check the limit around them, okay? So let's first just very quickly inspect this function. When could something potentially go wrong here? When could we potentially have a discontinuity? We could potentially have a discontinuity at x equals 1, right? Because then the denominator would be 0, and that's a problem because we cannot divide by 0 or we'll reach infinity. We'll approach infinity. But note that 1 is not in the domain of that particular function expression, right? So we don't actually care about it. However, as I mentioned, we need to evaluate the limit around x equals 1, and only if the limit is equal to the value at 1. So if the limit as x approaches 1 of f of x is equal to the value f of 1, then it's continuous, okay? So the function at that boundary point needs to have the same value as the limit around the point. If they're different, then there's a discontinuity, okay? So in this case, we already know that f of 1 equals 2, right? It just follows directly from here. When x is 1, the function is 2. Fantastic. Therefore, now when we start inspecting the limit needs to be 2 in order for the function to be continuous at 1, right? So how can we calculate the limit? Well, limit means x approaches 1. This is not a one-sided limit, so it could be either from the left or right. It needs to be the same. How can I calculate it? Well, I'm going to calculate it by using this function at the top. Okay, oops. Okay. Why? Because I said the x is approaching 1, but it's not exactly 1, so we're not going to be down here. We're going to be at the other case. It might be 0.999 or 1.00001, whatever. But it's different from 1, so we're going to be in that top case. Okay? By the way, I don't know why I wrote an equal sign. I don't need it. Limit as x approaches 1 of f of x is limit as x approaches 1 of 3x squared minus 4x plus 1 over x minus 1. Now, if I plug in 1, I'm going to have 3 minus 4 plus 1 at the numerator, which is, guess what, 0. Denominator is also going to be 0, so that's an indeterminate form. Therefore, I'll need to somehow rewrite it, right, in order to find the limit. What can I do? Well, at the top, I could try factoring this out. Now, this won't be that easy through the reverse Viet formulas, so I'm just gonna use the discriminant this time. So let me write this down. So the discriminant of this thing is gonna be minus 4 squared, which is 16, minus 4 times 3 times 1. I'm not explaining this in detail because that's quite back from like high school, so I hope you know it. 16 minus 12, which is 4. Therefore, x1 would be 4 wait, I forgot the formula actually. 4 minus square root of the discriminant, which is 2, over 2 times a, so that's 6. Therefore, we have 2 over 6, which is 1/3. And then x2 would be 4 plus 2 over 6, which is just 1. So now, when we square out the quadratic at the top, we would have 3 times x minus, x1 minus 1/3 times x minus 1. And then I could distribute here, right? So I would have 3x minus 1 times x minus 1. Once again, I know I didn't explain this in detail, but I assume you know how to solve a quadratic through the regular formula, so that's why I'm not doing it. If you have questions, please feel free to let me know. Okay, so going back, I'll just push this down a little bit, and I'm just going to use the factored form of my equation. So factored form is, I just need to keep the limit though. A limit as x approaches 1. And I'll keep the factored form here, 3x minus 1 times x minus 1 over x minus 1. Fortunately, I can cancel these out. Then I can just substitute 1 for x. So that's going to be 3 times 1, which is 3, minus 1, and that gives me 2. So the limit as x approaches 1 of f of x is 2. F of 1 is also 2, and because they're equal, this means that the function is actually defined at 1. Continuous, I meant. So what you can do, let me just push these like drafts somewhere below. So how you can write it is limit as x approaches 1 of f of x equals f of 1 equals 2. So because the value at 1 is the same as the limit as x approaches 1, that means that f is continuous at 1, right? That's the notation for continuity, or at least I think that's the notation the professor used. Generally, there are different ways to write it down. You could write it with words. If you don't remember that notation, you could just write literally f is continuous at 1. So that works too. And that's it. So that was the only not potentially, but like the only suspicious point, in this problem, right? And since we saw that the function is actually continuous at this point, we can just conclude that therefore f is continuous over the whole R, right? Because there's no other suspicious points to even check. It definitely is continuous over all other points. The only concern we had was x equals 1, and we proved that it is also continuous over x equals 1. So in this particular case, we don't have any discontinuities.